It's really a great pleasure to be back here at Berkeley. So today I want to tell you about what I think is a very exciting research program that I've been involved with over the past several years. And this, as Yasunori mentioned, this program is called the Conformal Bootstrap. It actually has a very long history, and I'll give you some sense of that history. But one of the reasons why the Conformal Bootstrap is very, very exciting right now is that it's currently making direct, precise quantitative contact with another area of physics, which has been around for over 150 years, called critical phenomena. So what I want to tell you about today is both what is the Conformal Bootstrap and how is it connected to critical phenomena. So to begin, I want to start with a typical phase diagram for a fluid. So everyone here is familiar with the fact that fluids like water come in different phases, solid, liquid, gas. And so if you look at the temperature, pressure phase diagram for a fluid, you see these different phases, solid, liquid, gas. And there's a line separating the liquid phase from the gas phase, across which evaporation occurs. But this line ends at a point called the critical point. And this occurs in essentially every fluid that you look at. There are hundreds of phase diagrams of materials that contain critical points. And so part of what I'm going to talk about today is the question of what happens at the critical point. And okay, there are many different avenues you can try to take to tackle this question. But first of all, let me mention that it can be probed experimentally. So this leads to a phenomenon called critical opalescence. And in particular, if you take a fluid, here is some sample of ethane, and you heat the fluid so that it approaches the critical point. You try to control the pressure and the temperature so it approaches the critical point. Something very interesting happens. If your fluid starts out as some clear substance, as you approach the critical point, it actually becomes milky white. Light has trouble passing through the fluid. And then once you go past the critical temperature, you enter this regime where your fluid is a supercritical fluid, and you see no sharp distinction between the liquid and gas phases. So let's ask the question, why does the fluid become milky white near the critical point? And physically what's happening is that, okay, this is a fluid at finite temperature. There are some thermal fluctuations of the fluid density. But these fluctuations occur over longer and longer distance scales as you approach the critical point. And in fact, you can try to quantify this behavior by looking at the 2-point correlation function of density fluctuations, delta rho. And what you see is that, okay, as you near the critical point, if fluctuations are very, very far apart from each other, then they're essentially uncorrelated. The correlation function falls off exponentially. But if the 2 points are sufficiently close to each other, then the correlation function has a power law behavior. That power law has an exponent, which is often written as 1 plus eta. And the transition between these two regimes occurs at a length scale, which is called the correlation length. Now, as you approach the critical point, what we believe happens is that the correlation length, in fact, goes off to infinity. It diverges. Fluctuations become correlated with each other over longer and longer distance scales. And in particular, once the correlation length becomes comparable to the wavelength of visible light, then these density fluctuations start interfering with light passing through the substance, and this is why it takes on the milky white appearance. Okay, so I said as you approach the critical point, the correlation length diverges. In fact, it also diverges with a power law behavior. As the temperature approaches the critical temperature at a fixed pressure, you can see it behave as T minus T critical to the minus nu power, where nu is some quantity that can be measured experimentally. In fact, okay, if you start probing, okay, what are these exponents, eta and nu, and you look at a wide variety of different substances. Here, this is a chart showing the critical temperatures and critical pressures of a range of different fluids. You see that, first of all, okay, the critical points occur over a vast range of different scales. Okay, several orders of magnitude separate the critical pressure in helium from the critical pressure in water. But in fact, in all cases where we've been able to approach the critical point and measure the critical exponents, we see that they come out to be the same numbers. Okay, and in some fluids, this is easier to do experimentally than in others, but they always seem to be the same. And this is an observation which is really crying out for some deeper understanding. In fact, the conspiracy is even weirder than that, because if you look at completely different types of materials, including magnets, which can be modeled by some three-dimensional lattice of spins which are interacting with each other. If you look at mixtures of different fluids, or if you even look at two-dimensional quantum systems, which can evolve forward in time. So these would be 2 + 1 dimensional quantum systems. Such systems are known to have quantum critical points, which occur at 0 temperature. And some quantum critical points in 2 + 1 dimensions exhibit the same critical exponents as you approach the critical point as you see in water and other fluids. So this is really a conspiracy. Okay, you see this vast variety of different substances, and they all seem to exhibit some sort of universal behavior at the critical points in their phase diagrams. So sometimes this observation is called universality. Well, okay, so how do we understand this? What's going on? Well, what are the properties of the critical point? Well, so one observation is that because the correlation length is going off to infinity, in fact, length scales are disappearing from the system. Okay, correlations between fluid density fluctuations look like power law behavior, look like a power law, no matter what separation the fluctuations are at. And this is signifying that there's really an emergent scale invariance to the system. Okay, if you zoom in on it, you still see some power law correlations between density fluctuations, and the system looks the same if you zoom in or zoom out. Okay, this is called scale invariance. In fact, it's believed, though not proven, that the symmetry, scale invariance, is enhanced to an even larger symmetry group. In particular, in many systems, it's believed that scale invariance combines with translation invariance, rotation invariance, and another kind of funny transformation called special conformal transformations to form a mathematical group called the conformal group. So what is the conformal group? The conformal group consists of all the transformations you can do to a grid of lines, which preserve angles, so which take 90-degree angles to 90-degree angles. So in particular, you can translate this grid, you can rotate this grid, you can zoom in or zoom out of this grid, or you can start shearing it in a way which preserves 90-degree angles. And these are called special conformal transformations, these angle-preserving shears. Okay, so if critical points have this big enhanced symmetry, the conformal symmetry, described by the conformal group, what does that imply for the physics of the critical points? Well, it does many things for you. Okay, so first of all, having conformal symmetry allows you to start organizing all the fields or operators in your theory according to how they transform under zooming in and out. Okay, so if I take my coordinates x and rescale them so that they become lambda x, then a field or operator in my theory, O of x, gets multiplied by lambda to a power, and that power is minus delta, where delta is some number characterizing the scaling dimension of the operator. In fact, these scaling dimensions are directly related to the critical exponents that can be measured experimentally. Okay, so if you know that the critical point is described by a conformal field theory, and you know the operators in this conformal field theory and their scaling dimensions, then you can write down all of the critical exponents that will show up as you approach the critical point. So this really helps us sharpen our goal. Our goal is to understand, okay, what is the conformal field theory describing the critical point in all these systems, and what are the scaling dimensions of its operators. And once we know that, then we can predict the critical exponents that can be measured experimentally. This way of organizing things, by the way, is useful for many other reasons. So, for example, you can ask, okay, if I have a system with a critical point, how many parameters do I need to tune in order to arrive at that critical point? Okay, so in water or other fluids, we know that we need to tune 2 parameters, the temperature and the pressure, to get to the critical point. In many magnets, we know that we only have to tune 1 parameter to get at the associated critical point. And in fact, the number of parameters that you need to tune to get to the critical point is in one-to-one correspondence with the number of operators in your theory with a scaling dimension smaller than the space-time dimension. Okay, so these are called relevant operators. And the fact that the phase space of water is 2-dimensional tells you right away that the conformal field theory describing its critical point should have 2 relevant operators in it. Okay, so this is one way in which thinking about things in terms of conformal symmetry helps you understand various features that we see in nature. Okay, so what is the conformal field theory describing the critical point of water and other fluids, as well as axial magnets and the quantum critical points I mentioned? Well, this has a name. It goes by the name of the 3-dimensional Ising model. Historically, the Ising model was written down as a lattice of spins, which can either point up or down, and they have nearest neighbor interactions. But okay, the continuum long-distance behavior of this lattice of spins is described by a field theory. And one way we can try to think about this field theory is in terms of a scalar field sigma, which has some set of interactions, like sigma to the 4th, maybe it has a mass term, and it has every other term you might think to write down in your Lagrangian compatible with the symmetries. In this case, we can impose a discrete Z2 symmetry, which takes sigma to minus sigma, which is why I've only written down even powers of the field. Well, okay, so this is a scalar field theory with a quartic interaction, much like the Higgs field of the standard model. But here we're in 3 dimensions rather than 4 dimensions. And we know that if we start tuning a parameter, then we should be able to reach the critical point. And in particular, there's a critical value of lambda over m, such that the long-distance infrared behavior of this theory is conformal. And we believe that it describes the physics of the critical points in water and other fluids. On the other hand, this critical point is strongly coupled. Okay, there's no small parameter. There's no way to use perturbation theory to actually calculate its properties. There's no extra structure like supersymmetry that you can use to help you understand what it's going to do. So this is a strongly coupled field theory, and because you can't use perturbation theory, you have to try to find other methods. So there's a whole list of other methods that people have tried over the years, epsilon expansions, high temperature expansions, different ways of truncating the renormalization group. All of these approaches have really a disadvantage that they tend to have errors that are not very easy to control. And so what I want to tell you about is another approach, the conformal bootstrap, which doesn't have that disadvantage. The advantage of the conformal bootstrap will be that we really can place rigorous error bars on quantities that we can compute. And moreover, it's going to take full advantage of the conformal symmetry that we believe exists at these fixed points. Okay, before I tell you about that, let me mention that the Ising model is not the only interesting 3D conformal field theory connected to critical phenomena. There are others. So one other interesting example is if instead of one scalar field, I have n scalar fields, I give those n scalar fields an interaction which preserves an ON symmetry rotating the n scalar fields between each other, so phi I squared. And this is called the ON model, 3D ON model. And in fact, different values of n are interesting. So the case with n equals 2, when there are two scalar fields, is believed to describe the superfluid transition in helium-4. In fact, this is a very interesting system to think about because there are, in fact, very precise experimental measurements that have been done in helium-4 as it crosses the superfluid transition. And in fact, some of these experimental measurements were done in space. Okay, so this is why I have a space shuttle here. There was a helium-4 experiment which was done in the 90s aboard the space shuttle STS-52. And it took a bunch of data for the heat capacity of helium-4 as it crosses the superfluid transition or the lambda transition. And from this data, you can extract power law behavior of the heat capacity as it crosses the transition. And from there, you can extract a critical exponent. And from that, you can infer one of the scaling dimensions in the O2 model. Okay, so we have this very precise experimental data that we can try to compare with. In fact, the O2 model also shows up in other very different looking systems, including two-dimensional superconductors, where we allow them to evolve in time. So any superconductor that has a standard Landau-Ginzburg description in terms of a complex order parameter will fall into this class. And these systems, we believe, have some 2+1 dimensional quantum critical points, which are also described by the O2 model, but in 2+1 dimensions rather than 3 spatial dimensions. So that's the only difference. But these are just related by some analytic continuation. Okay, other values of n are also interesting. So n equals 3 is a way to model sort of conventional isotropic ferromagnets like iron, cobalt, or nickel, where you have a system of spins, and the spins are free to rotate in any direction. Because they can rotate in any direction, there's an O3 symmetry in this system. Also, large n is interesting because why is large n interesting? Well, it's interesting because this actually gives a model which we can solve analytically in a 1/n expansion. We can solve for the scaling dimensions of all the operators order by order in an expansion in 1/n. So there are various places we can try to make contact with. In small n, we have experimental data. At large n, we can compare it to analytic calculations. And so we really have sort of a lot of information that we can compare any new theoretical technique to. Okay, more generally, there are lots of other reasons why it's interesting to study conformal field theories. Okay, not just these applications to critical phenomena. In 2D, there are many exactly solvable systems. These are nice to have. 2D CFTs also play a fundamental role in string theory. Okay, in 3D, there are many condensed matter systems. In 4D, there are many scenarios for physics beyond the standard model that have been proposed, which involve conformal dynamics. So to really evaluate these models, you need to know how 4D CFTs behave. And it's even interesting in higher dimensions. So for example, there's a 6-dimensional conformal field theory. Actually, it's a superconformal field theory. It has extra supersymmetry, which has gotten the theory community very excited in recent days. It's called the 2,0 theory. This is describing how many supersymmetries it has. But it's exciting because it's led to many, many new dualities that people didn't know about before. It seems to play an interesting role in compactifications and string theory. And so really there's a wide variety of different dimensions, different amounts of extra structure like supersymmetry that are interesting to study. Also, in any dimension, there's an idea called holography, or the ADS-CFT correspondence. Here, CFT is conformal field theory, which proposes that there is a duality between the dynamics of conformal field theories and quantum gravity systems in one dimension higher in curved space. So that's ADS is anti-de Sitter space. This is a space with constant curvature. And there's been really a large amount of theoretical work trying to understand the connection between quantum gravity in anti-de Sitter space and conformal field theories. But for me, I think this is really a beautiful and enticing concrete motivation to understand what CFTs can do. Because if holography is right, and if we can learn how to make really precise predictions in conformal field theories, then this is going to tell us a lot about quantum gravity. So I can say a few more words about this connection more towards the end. Okay, so I think this leads to an obvious big goal, which is, can we map out the space of conformal field theories, figure out what are all the different conformal field theories, and for each of them, particularly the ones that show up in real-world systems or other motivations, can we figure out how to predict their spectrum of scaling dimensions? Okay, this is what we're going to try to do. Okay, so now we come to the conformal bootstrap. This comes from the phrase pulling yourself up by your bootstraps, which is what this poor fellow is trying to do. And what's the idea? Well, the idea is to just use everything that you have on you to try to lift yourself up in the air. And in this context, what does that mean? This means how far can we get using mathematical consistency conditions that we know to be true with the fixed points? And so this idea can be made more precise. So the conformal bootstrap aims to use mathematical consistency conditions to map out and solve the space of CFTs. So what are these conditions? Well, first of all, we say we want to study conformal field theories. They have conformal symmetry. They also satisfy a condition called crossing symmetry, which I'll explain to you in a second. But it's related to the statement that the underlying operator algebra in this theory is associative. This is a very basic mathematical consistency condition for algebras of operators. And then the final condition is called unitarity, which in quantum theories encodes the statements that probabilities add up to 1. This is a mandatory condition. In statistical systems, it has an analog, which is called reflection positivity. And not every statistical system is reflection positive, but many of the most interesting ones are. And so this is a condition that we can impose. In particular, the 3D Ising model and the ON vector models, viewed as statistical systems in 3 spatial dimensions, we believe satisfy this condition of reflection positivity. So we can use it to our advantage. Okay, so this idea to use fundamental consistency conditions to solve CFTs actually had a beautiful success story in 2 dimensions. This goes back to work in the 70s by Ferrara, Gatto, Grillo, and Polyakov, and culminated in some beautiful results in the early 80s by Belev and Polyakov and Samologikov, which used the bootstrap idea to come up with exact solutions to an infinite sequence of 2D CFTs called the minimal models. So this idea really came to fruition in the early 80s. On the other hand, progress in more than 2 dimensions has been much slower. And it really wasn't until a recent revolution starting in 2008 that we really started to get exciting results using the bootstrap idea in more than 2 dimensions. So that's what I want to tell you about. Okay, so how does it work? Let me write down a few equations and give you an idea of how we set up the conformal bootstrap. Well, the idea is that instead of thinking about 2-point functions, which we discussed before, we can think about 4-point correlation functions. I have an expectation value of sigma of x1, sigma x2, x3, x4. I can ask, what does this 4-point correlation function do? And in fact, this is an object which gives you a very nice way to probe the spectrum of your theory, the set of scaling dimensions of operators that we're interested in learning about. Because it can be expanded in a sum over contributions from each operator in the theory, O. And each operator O contributes some function of the coordinates, which is called a conformal block. Okay, so what are these conformal blocks? Conformal blocks are known special functions. Okay, in some cases, they can just be written in terms of hypergeometric functions. In other cases, we have well-defined power series expansions that we can use to compute them. And they capture the contribution of an operator in the spectrum, O, to the 4-point function. It's labeled by the dimension and angular momentum, or spin, of the operator. And this kind of expansion is in many ways very analogous to expanding functions in spherical harmonics. This is something that many of you are probably familiar with. Except here we're expanding, if you like, in spherical harmonics of the conformal group rather than of the rotation group, which is what is ordinarily done. Okay, so there are many ways you can build on this analogy. Spherical harmonics are eigenfunctions of the Casimir operator of the rotation group. Conformal blocks are eigenfunctions of the Casimir operator of the conformal group. And in both cases, they satisfy some nice second-order differential equations that can be solved. Okay, so we can expand 4-point functions to probe the spectrum. On the other hand, there are different ways of doing this expansion. Or equivalently, we're starting with an object which is symmetric in all 4 of the points. But this expansion in conformal blocks doesn't manifestly have that symmetry. So if I require that an expansion is equal to itself under exchanging 1 with 3, I get a non-trivial consistency condition. I get the statement that a sum over conformal blocks of 1, 2, 3, 4 is equal to a sum over conformal blocks of 3, 2, 1, 4. And these are not the same functions. So this is a non-trivial consistency condition. And it probes the full spectrum of operator dimensions in the theory, at least all the ones which appear when I fuse 2 sigmas together. And the only unknowns in this expansion are the unknown set of scaling dimensions, as well as the coefficients in the conformal block expansion. So if you like, this equation is a very non-trivial constraint involving sums over special functions that we can try to extract information from, including what are the allowed values of the deltas and the lambdas. Okay, well, so the realization in 2008 is that this is a problem that we can tackle numerically. It's not so easy to tackle it analytically, but we can, but I should say some progress has been made analytically. But some of the most exciting results have come from putting this equation on a computer. And the idea is that we can take this equation, which is a function of the different coordinates, and apply some clever functionals to it. Functionals take functions to real numbers. Okay, so if we apply a clever functional to this equation, after making some assumption about the spectrum, like there's a gap in the spectrum which starts at some number, 3.7, we might be able to find a functional which turns this into an equation like 0 equals a sum over strictly positive terms. And then you have a contradiction, and that means that whatever assumption you made has to be wrong. Okay, so by making assumptions, looking for functionals that would lead to a contradiction, you can start mapping out the allowed space of scaling dimensions. Okay, so concretely, this is something we can tackle using convex optimization. So there are techniques called linear programming or semi-definite programming in convex optimization. This is concretely what we do. And so we tell a computer, okay, scan over some space of possible linear functionals. In the plots I'm about to show you, this involves something like a 20-dimensional space up to a 1200-dimensional space that we tell the computer to scan over. And because we have to do this scan or equivalently solve a convex optimization problem for each point in our plot, each plot is going to come from solving something like order 1,000 optimization problems, one for each point. So to do this efficiently, we run these 1,000 optimization problems on a high-performance computing cluster so we can do them all simultaneously. OK, so now I want to show you a bunch of plots. Before I do that, let me just mention that the state of the art in this procedure is a program called SDPB, which is an efficient, high-precision, semi-definite programming solver written by one of my collaborators, David Simmons-Duffin. And he's made this program freely available for anyone to download. So anyone who wants to get involved in the Bootstrap numerically can go and download SDPB. OK, so let me show you some plots. The first plot I want to show you is one of the most exciting ones that came early on in this program. So this is from work done in 2012. And the idea is, OK, we look at a 4-point function, sigma, 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 sigma. We look for a bound on the scaling dimension of the first operator that appears in the conformal block expansion of this 4-point function, delta epsilon. And so we can place an upper bound on delta epsilon as a function of delta sigma, using this procedure of finding a clever linear functional that excludes points above this bound, but allows points below this bound. And here, this is actually a sequence of bounds that come from telling your functional to have a larger and larger search space. So you get stronger and stronger bounds. But it's important to know that at each stage, you get a rigorous and true upper bound, and they just get stronger and stronger as you increase the functional search space. So this has some interesting features. First of all, it starts at some nice values, 1/2, 1. In fact, these are the scaling dimensions which occur in a free field theory in 3 dimensions. Okay, so a free field theory, non-interactive field theory is an example of a conformal field theory. It's just a very trivial one. So that sits in this corner. On the other hand, you also see that there's some funny structure here. The slope is different over here than over here. Maybe there's some sort of funny kink in the upper bound. And what's going on there? Well, it turns out, this really should come as a shock. It turns out that the 3D Ising model sits right in this kink. How do we know that? Well, there are fairly precise measurements of the scaling dimensions, or critical exponents, coming from lattice simulations, as well as measurements in experimental systems. And so these are some of the best numbers that have been determined from lattice simulations. And in fact, these numbers, 0.518, 1.41, sit right in this kink. So somehow, and remember, in this Bootstrap equation, we said nothing about what theory we're talking about. We're just writing down equations which are true in general CFTs. And yet somehow this completely general equation knows about the existence of a 3D Ising model. And moreover, it sits right on the boundary of the allowed region and in some funny corner. So now we can try to, well, first of all, you can try to use that to your advantage. You can say, where is the kink located? We can say, the location of this kink gives me some prediction for the scaling dimensions. Yeah, that's something you can try to do, but it's okay, it's not so rigorous. I mean, if you zoom in on this, then it starts smoothing out because it's found numerically. And so it looks very intriguing, but it's hard to know what you can say very precisely. On the other hand, it turns out that you can even do much better than these upper bounds. Because if instead of just the sigma 4-point function, you look at a system of 4-point functions, sigma, 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 epsilon, 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 epsilon. Write down all of the crossing symmetry equations that come from expanding this system of 4-point functions in conformal blocks. And impose a very mild condition, the condition that sigma and epsilon are the only relevant operators in the theory. This is the statement that the phase space of water is two-dimensional. By putting in this information, we discovered a couple years ago that, in fact, this leads to a rigorous closed island around the Ising point, rather than just an upper bound. Okay, so here we see this is at a fairly small search space for the functional, 105 components, but you see that there's an island over here, which is allowed, and is disconnected from some larger bulk region. So now we can ask what happens to this isolated island as we increase the search space of the functional, as we push this program more and more. And what you expect is to see that this island starts shrinking. And then you can ask, how small can we make the island? So what I want to show you is actually a video of what happens when you increase the functional search space and start zooming in on the island. And here in this video, you're going to see us going to from this 100 components to 1,265 components. And the result is actually fairly dramatic. Okay, so you see the island getting smaller and smaller as we increase the number of components, getting smaller by orders of magnitude. Here you see the Monte Carlo lattice results, but our Bootstrap island is getting even smaller than that. And is an order of magnitude smaller than the Monte Carlo now. And then, remember, this is a rigorous island. We just put in conformal symmetry, basic consistency conditions, plus the statement that there are two relevant operators. And this is what's allowed. Was there a question? I don't know if there's any fundamental limit. Right now, this is really an experimental question. We don't have the theory which tells us, as we double the number of components, how small will this region shrink. And in fact, we've seen different behavior. I'll show you what happens for the ON models in a second. And there you see a different kind of behavior as you increase the number of components. So that's currently not known. But OK, we see the region keeps shrinking. And in fact, our best results, here's another view of our current best results, which is in work that has yet to be published. But here's a view of the Monte Carlo values. Here is the Bootstrap island. This is showing a zoom in of those points. And the error bars are currently in the 6th digit for delta sigma, the 5th digit for delta epsilon. And we can similarly get extremely precise measurements of the coefficients lambda between sigmas and epsilons. So I think this is really a striking success story, which shows the power of the conformal bootstrap in 3 dimensions. And it's natural to ask, OK, what more can we do? So one other very interesting class of theories are the ON vector models, as I mentioned before. And we could try to repeat this analysis. So for example, in a theory with an ON symmetry, we have operators which transform in representations of ON. So phi carries an ON index I. This is a vector. And we can look at 4-point functions, phi I, phi j, phi k, phi l. And similarly, start placing bounds on the leading ON singlet appearing in the expansion of this 4-point function. So that's what this is showing. This plot is showing, and it's showing it for different values of n. So here was the Ising bound that I had before. The next one is the bound for the O2 model, O3 model, O4 model, all the way up to the O20 model. At large n, I mentioned that we can do analytic calculations in a 1/n expansion. That's what's shown in these black pluses. And in fact, you can see that the black plus corresponding to the O20 model sits right in the kink that we see in the numerical bound. Okay, and for the O10 model, it's also very close. At small values of n, we can't use this large n expansion. That's the dashed line. It sort of starts doing very badly. But we can compare to precise experimental measurements. For the O2 model, we can compare to measurements of the heat capacity of helium-4, which extract the critical exponent. For the O3 model, there are measurements in ferromagnetic systems. And also in both of these cases, there are lattice simulations that people have done. And at small values of n, you can see that those experimental, the best experimental results also seem to sit right in these kinks. Okay, so now let's go further. Let's go to a mixed system of correlators containing both the ON vector phi I and the leading singlet S. We managed last year to study the Bootstrap equations for the system of correlators and see a sequence of islands, much like we had the island for the Ising model. Okay, so these islands you can see are so far not nearly as small as they were for the Ising model island. We hope this is going to improve as we push the computations further, increase the functional search space, and add more Bootstrap equations. But let me just give you a sense of how these determinations compare to various experimental determinations. So here's a zoom in of the O2 island. So these are a sequence of Bootstrap islands from increasing the functional search space. This yellow rectangle shows the best Monte Carlo simulations. You can see that those are very, very precise, and our Bootstrap island isn't yet competitive. We can also compare to helium-4 measurements, which are shown in this band. In fact, they just measure one critical exponent, which translates into the dimension of the singlet. And these are showing the 1 sigma and 3 sigma confidence intervals in the experiment. And actually, you can see that there's currently a discrepancy between this experimental measurement in helium-4 and the best Monte Carlo simulations. And taking the error bars at face value, this is something like an 8 sigma discrepancy. So one very, very concrete goal for the Conformal Bootstrap program right now is to shrink this island enough so that it can resolve this 8 sigma discrepancy and decide who is right and who is wrong. Let me show you one other interesting result. This is one experiment. This is one experiment. So remember, this was done in space. So terrestrial experiments aren't as competitive. But by the way, the reason that it's done in space is because when you have a fluid, there's typically a pressure gradient, which makes it very hard to have the whole fluid sample reach the critical point. And so going into space helps reduce the pressure gradient coming from gravitational effects. Okay, let me show you one other application in the O2 model, which is that in addition to constraining scaling dimensions, we can also constrain coefficients appearing in correlation functions. So one interesting coefficient comes from looking at the 2-point function of the current. Okay, this is an O2 global symmetry current. Its 2-point function is proportional to some number, which is sometimes called, in theoretical circles, it's called the current central charge. In condensed matter circles, this is a number which is directly related to high-frequency conductivity. And in particular, in 2+1 dimensional superconductors, these have a quantum critical point. And if you look at the conductivity of the superconductor when it's in the vicinity of the quantum critical point, this is related to the current 2-point function. The Fourier transform, this gives a function of frequency. And the high frequency behavior of that function is directly related to this coefficient. So using the Bootstrap, we can relate, we can get a rigorous island for this coefficient Cj in the current 2-point function. This translates into a determination of the high frequency behavior of the conductivity, 0.3554, with an error bar in the last digit. And this can actually be compared to recent quantum Monte Carlo simulations that have been done by various groups, which give numbers like 0.355, 0.360, which at first sight looks a little bit worrying given this error bar, but I've been assured by these authors that this is just the statistical error, and there's a systematic error in these computations, which is at the level of a few percent. So it looks like these numbers are all very consistent with each other, given those systematic uncertainties. Okay, so before I conclude, let me just mention that there are many other places where you can try to do the bootstrap, including not scalar correlators, but fermion 4-point functions. You can also do it in supersymmetric theories, and so on. And in fact, there are some situations where we've computed bounds from the bootstrap, we've seen some kinks, and we don't yet know how to interpret them. So an optimistic reading on this situation could be that maybe the bootstrap has discovered interesting new CFTs, and previously theorists weren't clever enough to understand what these CFTs were. So I think there's at least some chance that the conformal bootstrap here can really be used as a discovery tool for finding interesting new theoretical structures. So I just wanted to mention a couple examples. One comes from looking at the fermion, the bootstrap for fermion 4-point functions in 3D. Here we see a kink. Another comes from looking at the bootstrap in 4-dimensional theories with minimal supersymmetry, or n=1 supersymmetry. Again, we see a kink. It's not completely obvious in this plot, but there are other plots you can make that make it clear that there's an interesting discontinuity going on at this value 1.41. And there's a possibility that we're discovering new theories in the bootstrap. Of course, these all need to be studied much more carefully, and it'll be very interesting to see if we can turn these discontinuities and bounds into rigorous islands and make precise determinations of the properties of these theories. Okay, so where do we go from here? Okay, there are many things to do. One obvious direction, as I said, is to make our predictions in the ON models more precise. We can try to resolve this 8 sigma discrepancy between Monte Carlo and experiment. We can also try to make precise predictions for other operator dimensions, which translate into subleading corrections, critical exponents corresponding to subleading corrections that can also be measured, though it's harder experimentally. We'd also like, okay, we know from thinking about quantum field theories over the years that there are many other interesting CFTs out there, for example, built out of fermions and built out of gauge fields. And it would be great to find more islands. Really, we'd like to find some tiny precise island for every CFT that exists. Okay, that's a goal. But there are many theories we know about, and we can try to hone in on them more. So one interesting example is the three-dimensional analog of QED. Okay, when there's a theory with a U1 gauge field coupled to fermions. In fact, this theory is believed to describe the physics of quantum spin liquids, which are an interesting state of matter. Another interesting example is 4-dimensional QCD. Okay, we know QCD in the real world confines along distances and produces a spectrum of protons and neutrons and pions and other bound state particles. But if you take 4D QCD but vary the number of quarks and vary the number of gluons, in fact, we believe that for some values of the number of quarks and gluons, the theory doesn't confine and has conformal behavior at long distances. It's actually been a long-standing question, which is still not resolved, of where this transition from confining behavior to conformal behavior occurs. And I think there's really a hope that in using conformal bootstrap techniques in 4-dimensional CFTs, we can really hone in on the conformal window of 4D QCD, and optimistically we'll find little islands corresponding to each theory in the conformal window, and we can just count islands and see, okay, how many theories are there in the conformal window, and when do we start having confining behavior? So this is another very exciting goal for the bootstrap right now. Okay, of course, there are these mystery theories, which we don't know how to interpret yet. That's one exciting direction. Also, there are other maybe non-Lagrangian theories that it's very hard to study theoretically. One example of this is the 6D 2,0 theory. That's very exciting in the theory world right now. And there are lots of other supersymmetric theories, like 4D n equals 4 supersymmetric Yang-Mills theory, which is being intensively studied in the context of scattering amplitudes, that the bootstrap can say something about. And people have already started working on this. So finally, let me mention one other interesting future direction that we're starting to set up, which is to bootstrap the stress energy tensor. Okay, the stress energy tensor is an operator in every local conformal field theory. It tells you how the theory transports energy. It really plays a fundamental role in the structure of the theory. It tells you how to couple the theory to gravity. And by studying the stress energy tensor, first of all, you can learn about universal constraints on all CFTs, because all local CFTs should have this operator. And secondly, it's a very interesting object in the context of holography, because the stress energy tensor is holographically dual to gravity, the graviton, okay? Living in anti-de Sitter space. So for example, the 2-point function of the stress tensor has a coefficient in it. That coefficient is directly related to the Planck scale in ADS gravity. And so by constraining that coefficient, you can place constraints on the strength of quantum gravity. Okay, so there are all sorts of exciting connections like this, where it really looks like by studying precise properties of CFTs, and in particular the stress energy tensor, we can learn a lot about quantum gravity using holography. So let me just end by saying, we're at a really exciting moment right now, because I think we're really starting to map out the space of CFTs. We're starting to find different islands. And pushed to its logical extreme, I think we really can start creating a detailed map of theory space. We can find all the different islands around the CFT world. And we can do CFT cartography. And we might even discover completely new theoretical structures or a completely new continent that we didn't know about before. So thank you very much for your time. And I'll take any questions. When you look at non-minimal models in 2D. Yeah. The 2D bootstrap, it found all the minimal models. But I think there's really a lot of room right now for exploring the space of non-minimal models. And currently it's underexplored. So for example, one thing you can do is we can repeat this procedure in 2 dimensions, start computing bounds on scaling dimensions in 2 dimensions. Actually, you do see a kink. The kink corresponds to the 2D Ising model, which is one of the minimal models. And you see the other minimal models like saturate the bound in various places. But this is also a space where non-minimal models have lived. So far, we haven't found any obvious positions where non-minimal models would live, but I think it's still very underexplored. Yeah.
In most cases, you see these tiny islands, presumably formed like islands on the amount model. But for the Opal model, you showed that there's an extended region around the model. Is there a reason you don't see any extended regions of possible models for the other cases than there?
Oh, sorry, but by extended region, do you mean, let me make sure I understand. You mean this region? No, that's also there in the ON models. It's just further to the right. So it's not shown on this plot. And in fact, that whole extended region is something which is currently underexplored. And here you can get a sense of what it looks like at a small search space. But we really haven't mapped it out at a large functional search space yet. And in fact, the big open question is how far does this recede to the right? Because if you could show that this bulk region, say, receded to the right, maybe all the way out to a scaling dimension of 3, okay, optimistically, then you would really see that the Ising model is the only solution with 2 relevant operators. Okay, so this really starts to put this idea of universality on a rigorous footing. So, and concretely, that's the question of how far can this region be pushed to the right? Yes. Yeah, that's also an exciting thing. So, yeah, so it depends on what assumptions you make. So here, here there's still a hope that the Ising model is the only model with just these 2 relevant operators. I think known theories with critical lines don't.
But if you drop that assumption, then absolutely.
Symmetric theories with conformal manifolds that have lines that you can move, or even higher dimension spaces that you can move around on by adjusting couplings. And all those spaces, I think you could potentially find in the Bootstrap. So actually, there's a group of people right now trying to understand this in the context of 4D n equals 4 super Yang-Mills theory, which has a critical line associated with adjusting the coupling, because we believe it's conformal at any value of the coupling. And so the hope is that using the Bootstrap equations, you can really map out that conformal manifold. It's not the square root of 2, unfortunately. So I think we can probably see that here. Yeah, so this is not compatible with the square root of 2. So, but yeah, I mean, it's a really interesting question. Now that we're starting to get very precise determinations of these numbers, can we guess whether there's some analytical equations for them? And so far, we haven't guessed anything that looks reasonable, but I think there's still a hope that there could really be an analytic solution. So part of this is trying to get data for that.
So you showed us that when you consider only one operator, you get upper bound.
Yeah.
When you go to 2,
Yeah.
So what is the reason why items should always correspond to things where you drop from the operator?
So it's actually not, it's not just adding more correlators. So if you just look at the crossing relations for these correlators, also here we've imposed a Z2 symmetry, so that's one extra assumption. Then without any other assumptions, the allowed region is almost the same. You still see an upper bound with all this allowed, but it's then when you input the statement that there's a gap in the spectrum, so sigma and epsilon are the only relevant operators, that you carve out all of this region. So it's that extra information that's doing the heavy lifting.
My question is, why do the items always reduce back to kinks, not an average point on the boundary?
That is currently an open question. Yeah, so that's, yeah.
Maybe the only theory has a break,
Right.
Right, and in fact, in this space, the ON models also satisfy this bound, but they live in the interior of the space. So you really have to put in the information that there's an ON global symmetry before you start to see them living on the boundary of the allowed region. So it's really not at all obvious. So we know there are other solutions in the interior. And then the question is, how much information do you have to put in to really start to isolate those solutions?
Two things you mentioned all of them. Very fantastic. So you mentioned just one is a conformal window in using one program, which has been a long time study that is.
Yes.